today our topic is phase modulation, and we will actually see the signal waveform which belongs to this M-array digital modulation scheme, and actually the phase of the signal is varied, or the phase of the signal or the phase of the waveform differentiate between the signals. So we would actually see the M waveforms, or Sm of t. We will see its mathematical expression, and then we would be interested to find out the average symbol energy, which we denote by E sub average energy of the waveform, and the average bit energy, which we denote by E sub b average. And then I would like to derive a mathematical expression for Euclidean distance between the signal waveforms, or between the adjacent symbols. We say adjacent symbols. So keep in mind, we have the M-array modulation scheme, and you are familiar that this m is equal to 2 raised to the power k, right? K is integer. You can have k 1, 2 and so on. So you have the values of m, maybe 2, 4 and so on, right? So we will discuss this M-array digital modulation scheme, in which only the phase of the waveform varies, and the different symbols are differentiated by different phases. So let me write mathematical expression for Sm of t, which is the waveform for the M-array phase modulation signal, and we represent it. It's the real of g of t, which is pulse shaping waveform, e raised to the power j 2 pi m minus 1 over n. These are the different phases, and then you have e raised to the power j 2 pi f ct, right? So this is the this is our signal. So this is our signal Sm of t. So Sm of t is we can represent Sm of t as the real of this waveform. Now let me discuss it in more detail. I'll discuss this waveform, each and every part of this signal waveform, and then we will go ahead to further derive other expressions. So if you observe it, before going to more derivations, let me recall the Euler identity, and you are familiar with this identity, that this is it can be represented by this way. Now if you want to find out the magnitude of this Euler, it is unity, right? It is 1, and the phase of this is theta. Similarly, when we say the real of e raised to the power j theta, it simply means we are talking about this term, cos of theta, right? So we are just talking about this cos of theta. Okay, with this in mind, when you say e raised to the power j theta is multiplied with another exponential e raised to the power j beta, so it simply means that you have e raised to the power j theta plus, you can rewrite it like this. And if you are interested on the real part of this thing, the real part is cos of theta plus beta, right? So you can write it like this. So these mathematical identities are important. Similarly, you are also familiar with the cos of alpha minus beta, cos of alpha trigonometric identity, cos of alpha minus beta, which we will use to explain these expressions. This is cos of alpha, this is cos of alpha, cos of beta plus sine alpha, sine beta. So this mathematical trigonometric identity will also be helpful for today's lecture. So now let's go back to our signal, and let's see how our signal is represented. It is represented as the real part. I will rewrite it for you. So it is actually the real part of g of t, which is just a usually it is taken as a gate pulse, right? A square pulse is g of t. The simplest one is the square pulse, a waveform, just a waveform which is just like this, a square pulse, right? Between 0 and time interval with a unity amplitude. It can be any amplitude, right? You can just generalize it to be a. It's up to you. So it's g of t, the real of g of t. Then you have another term which is e raised to the power j, and with the j you have 2 pi m minus 1 over capital M, right? This capital M is as I said earlier, it can be 2, it can be 4, 2 raised to the power k, it can have any value. And this small m, it distinguishes each symbol. See, this m appears here also. So this is the only difference in different symbols. You will see it just in a short while. And then you have e raised to power j 2 pi f c t, right? So this is your signal waveform, which is represented in this form. So let me explain it further. We say that, okay, the real of this means we are actually talking about just the cos. Now this is, if you observe here, this is just the carrier, 2 pi f c t. This magnitude is unity and frequency is fc, because we are just talking about the real part, so it means cos of 2 pi f c, right? Similarly, the real part here, so cos of 2 pi m minus 1 over n, and g of t. Of course, g of t is a real signal. So when we say the real part, g of t, we know that g of t is real signal, right? It may be a square pulse, which is a real signal. So we are left with, we can say that actually we are talking about g of t, and I can say cos of 2 pi f c t, 2 pi f c t, which is from here, the real part, and then this is just like cos of alpha, and this is plus beta. So let me write it, plus 2 pi m minus 1 over n, right? So this is your Sm of t, the M array, the waveform for M array phase modulated signal. And what is this small m? This small m is, this is 1, 2 up to capital M. So if capital M is 2, then it will be only 1 and 2. If capital M is 4, it will be 1, 2, 3, 4, right? So you have 4 waveforms. when m is 2, you have two unique waveforms, and those waveforms differ by this phase only, because the rest of the part is same. This is just the phase which varies this m. So S1 of t with the m1, S2 of t, m would be 2 here, S3 of t, m would be 3 here, S4 of t, m would be 4 here. So you can differentiate different signal waveforms by different values of m, and these values of m actually they represent a different phase for the for this signal, different phase. Because when we talk about the phase, keep in mind we always try to draw our signals in the Euclidean space. In Euclidean space we have basis functions, right? So you can have phi1 of t, phi2 of t as the basis function, and you can say, okay, I have some angle, I have this point which has certain phase, So this point, signal point, can be represented with this phase as Sm of t. Is a signal point. So similarly, another signal point will have another different phase, another signal point will have different phase, another signal point will have different other phase. So you have different phases. So you can draw as many signal points on this circle as you want, depending upon these values, the capital M value and the value of capital. If you have M4, 4 points. If you have capital M is 8, then you have 8 points on this circle, right? So we will talk about these later on. So now it's quite clear now, this expression, that you are actually talking about this real part of these exponential, actually talk about this carrier frequency which is certain, this type, some waveform, right? Carrier frequency with some certain angle, and this is multiplied with a gate pulse. So if you multiply it with a square gate pulse, right, something like this, so actually you will be left with just, because this is just the scaling factor, right? So it will just scale the amplitude of this waveform. So it will scale the amplitude of this waveform, right? And you will get the same sinusoid. So the waveform would be something like this. We will see it later on. So let me move this slide further, and we will see our signals. Now we already let me write it here. We say that our signal is Sm of t. Our signal Sm of t is g of t, and then we have cos of 2 pi fct plus 2 pi m minus 1 over m, right? So you can also rewrite it in this form. G of t is cos of alpha plus beta. It's in the form of cos of alpha plus beta. So you can say, okay, cos of 2 pi fct cos of 2 pi m minus 1 over m, cos of alpha cos beta, right? And then sine of alpha minus g of t sine of 2 pi fct and sine of 2 pi m minus 1 over m. So cos of alpha cos beta minus sin alpha sin beta. So you can rewrite your Sm of t in this form as well. Now if you see the phase of this waveform, the phase for the Sm of t, the phase theta m for Sm of t is actually 2 pi m minus 1 over m. So this is the phase of Sm of t, or the mth signal waveform. So this is the phase of the mth signal waveform. Now we usually, when we say that we have capital M, we have capital M symbols, because we have M array modulation scheme. We have capital M symbols. So our capital M can be 2 raised to the power k, and our small m, it is from 1 to capital M. It is from 1 to capital M. So we have m possible phases of the carrier that convey the transmitted information. M possible phases of the carrier conveys the transmitted information. So if you have, for example, if you want to transmit some sequence of binary digits 1 0, and you have capital, you suppose that your capital M is 2, so you will have two waveforms to transmit these two unique waveforms. So when you have two unique waveforms, you represent one by one waveform, suppose 1 by S1 of t and a 0 by S2 of t. So if this is your data, if this is your sequence, you would transmit S1 of t, then you would transmit in first time interval, then you would transmit S2 of t in the second time interval, then again in the third time interval you have to transmit S1 of t, and in the fourth time interval you have 0, so you need to transmit S2 of t, and then you have in the fifth time interval and sixth time interval again S1 of t. So S1 of t and S1 of t. So this way you can transmit this information from transmitter to the receiver, from transmitter to the receiver. Now we are interested in finding out the energy of our signal, right? So the energy of our signal. How do we find the energy of the signal? So we find out, when we are interested in the average energy, we always square our signal. We square and integrate it over a period, right? So you integrate it over a period. So if you try to square it, what do you get? 0 to t. You have g square t and cos square and whatever it is. Let me write it like this. Okay, right? So this is this is how you can find out the average energy in this waveform, average energy of this waveform. So if we want to find out the average energy, we can write it like this: 0 to t. We have g square t, and here you can write this square as cos square theta 1 plus. You can write it 1 plus cos 2 times theta over 2, right? And dt. You can rewrite it in this form, and if you now you can write it like this. It is g square t over 2 dt plus 0 to t g square t cos 2 theta over 2 dt, right? Now let me solve it further. And from here you can see that this is half 0 to t g square t dt, and this term, the second term is the now let me if you evaluate it, you will get 0 actually. But how do you get 0? Let me tell you a little bit about that 0. Now if you see, this g square multiplies with a cosine term, and a cosine term, if this g square is some pulse, which we just say that it is a pulse of amplitude a, suppose if it is a pulse of amplitude a, so this is some positive level, right, between this 0 to t. So you are actually this thing can come out, this is some positive level, so a square over 2 will become outside of this integral. It's a kind of constant, and then you are left with just cosine wave. Okay, and a cosine wave, whatever is its frequency and phase, if you integrate it over a period, you will get 0. So actually this term integrate out to be 0. You can try this one to multiply and integrate it, but in the end you will get 0. So what actually you are left with? You are left with what is this? This is the energy of the pulse. Whatever is the energy square of the signal over the period is the energy of the pulse. So you are left with this. So your average energy of the waveform, or average symbol energy, we call it the average symbol energy, it is Eg over 2. This is your average symbol energy. Now if this is our average symbol energy, each symbol carries how many bits? K bits, right? Each symbol, each Sm of t, each Sm of t carries k bits, right? Each symbol carries k bits, and this k is, you can find it out from m is equal to 2 raised to the power k. So your k is log m to the base 2. So when each symbol carries k bits, and you are interested in the bit energy, the average bit energy, you already have the average symbol energy. You divide it by k, right, and you will get the average bit energy, which is equal to Eg over 2, and for this k, but we can write log m to the base 2, So our expression turns out to be Eg, our expression E for the average energy, average bit energy is Eg times Eg to log m to the base 2. So this is our expression for the average bit energy. So the average bit energy expression. Now if you observe your signal, it is in the form of cos as well as sine, right? You have a cos and a sine waveform. If you see, we expanded our signal. Let me go back to the actual original signal and I'll show it to you. If you see our signal right in the beginning, we wrote our signal in the form of sine and cos, right? So if you see over here, this one, sine and cos, you see, we have sine of 2 pi f ct. If you see here, concentrate on this part, we have cos of 2 pi f ct, which is a carrier, sine of 2 pi f ct, a carrier frequency. And keep in mind, this sine and cos of 2 pi f ct are orthogonal. So these are actually two orthogonal carriers. and these orthogonal carriers are added together. This orthogonal carrier, the first one, cos orthogonal carrier, is scaled by this term, and sine carrier is scaled by this term, and these two are added, right? A subtraction means just a minus sign and you add the two, right? So these two are actually added. So if you go back to your signal concepts, now we can use the basis, we can represent the signal waveform as the sum of two orthogonal carriers, scaled orthogonal carriers. We can represent these as the sum of two scaled orthogonal carriers. So we write that if our psi1, let me write our psi1 of t, it's a basis function, right? The basis function, and it's Eg g of t cos of 2 pi fct, cos of 2 pi fct. So this is our the first basis. Now if you try to find out the energy of this signal, this phi1, you will end up with the unity. Its energy is unity. You can find out its energy and you will end up with unity. Similarly, psi2 of t, these are orthonormal basis functions, 2 over Eg. Now here the negative sign is there, which is to facilitate the expression, minus g of t, and we have sine of 2 pi fct. Now these are our two orthogonal carriers with unit energy. If you are interested to find out its energy, just try to integrate it. Like if you are interested in finding out the energy of phi1, it would be phi1 square dt in this interval, right, 0 to t. So if you integrate it, you actually get the unity. Try to integrate it. Let me do it for you. So if you integrate it, you will get 0 to capital T, and then you have 2 square, 2 over Eg, square root cancel with the square, and then you have g square t cos square 2 pi fct dt, right? Then you are having this is the energy, so let me write it outside this way, 0 to t g square t, and this can be written as 1 plus cos 2 and whatever is inside whole divided by 2 dt, right? You can write it in this form. Now let's solve it further, and this is 2 over Eg, and you will get g square t over 2 dt, 0 to capital T, plus another term is g square 2 over 2 cos of 4 pi fct, okay, dt. Now from this here, these two actually cancel out from here, so you will be left with 1 over Eg 0 to capital T g square t dt. This thing again a sinusoid multiplied with some constant. Usually if you take it as a square constant over a period, it turns out to be 0. So this is actually 0, and you are left with 1 over Eg, and here this is also the energy of the gate pulse, G square T integral 0 to T. So now we can see that actually this energy is equal to unity. So the energy of phi 1 is actually unity. Similarly, you can derive it, you can verify it for phi 2 as well, that the energy of phi 2 is also unity. Now when you get these orthonormal basis functions, with these orthonormal basis functions we can actually plot these two axes. We say, okay, is our phi 1 of t first axis and this is our second axis, right? And we can represent our signal as m of t, which is actually cos of 2 pi m minus 1 m. Let me write it for you. And then I'll explain. We said that our Sm of t is actually g of t cos of 2 pi m minus 1 over capital M, right? G of t cos of 2 pi m and cos of 2 pi f ct, right? Then you have a negative sign g of t. You have sine of 2 pi m minus 1 over capital M and sine of 2 pi f ct. Now if you see this one, we can write it as in the form of, we can write it in terms of phi 1. So to write it in terms of phi 1, what we can do, we can say that, okay, this term, you have this phi 1, you have phi 1 of t, but then you need to multiply the under root Eg over 2, because it has, see, let me write it this way. You have, let me write it and then I'll explain, right? Let me write it for you. It can be this whole term can be written as under root Eg over 2 cos of 2 pi m minus 1 over capital M and phi 1 of t. Now you are familiar with the phi 1 of t, which is under root 2 over Eg. So 2 over Eg and g of t. So 2 over Eg will cancel out this term. 2 over Eg will cancel out this term, and you will be left with g of t cos of 2 pi m minus 1 m and cos of 2 pi f ct. So it's easy to understand, right? It's easy to understand that we can write it in this form. So this waveform, so this term, we just write this term as this one, and now the second term minus g of t. Now this you can see sine of 2 pi f ct and g of t. G of t is already there in phi 2 of t, and there is another scaling term which is under root 2 over Eg. So you need to multiply this with Eg over 2, E sub g over 2. So this will cancel out, and then you are just left with sine of 2 pi m minus 1 over capital M. Right? So this is, and the negative sign is already there in phi 2. The negative sign is already there in this phi 2. as we saw. So you can write this whole expression, you can write this whole expression, this one, the second term, as under root e sine 2 pi m minus 1 over capital M Eg over 2 phi of 2 t. So this is how you write your signal. You write your signal as a sum of phi 1 and phi 2, as a sum of phi 1 and phi 2. Now if you observe it closely, this expression, just if you simplify it, this expression can be written as I can say that, okay, you have a phase term which depends on AM1 phi 1 of t. I can write it like this, right, plus AM2 phi 2 of t. So your Sm of t is just represented by this AM1 and AM2. These are the actually they scale phi 1 and phi 2, and you can say that the vector form of your Sm, if you want to write the vector form of your Sm, it is just AM1 and AM2, these coordinates, and you are familiar with these coordinates, as we just saw that this is under root Eg over 2 cos of 2 pi m minus 1 over capital M, and this is Eg over 2 sine of 2 pi m minus 1 over capital M. So your AM1 is this one, and AM2 is actually this two. Now with this representation, you can represent your signal. In this Euclidean space with the axis phi 1 and phi 2. And you have just, if both AM1 and AM2 are positive, the point will be somewhere here. Both the coordinates are positive, right? This is positive and this is positive. If x-axis is negative and the other one is positive, your point will lie somewhere here, right? And so on. It can be here, it can be here, it can be here, it can be here, depending upon your AM1 and AM2. So these are you can represent your signal as a point in signal space. So in the vector form, we say our Sm in the vector form is given by this. This is the vector form of our Sm. Now if you have now we can see that with this vector form, we can see that our signal, the phase modulated signal, is actually two-dimensional. We need phi 1 and phi 2 to represent phase modulated signal. So this is the dimensionality of our phase modulated signal. A phase modulated signal is actually a two-dimensional signal. So we have when m is equal to 2, we call it binary phase shift keying, and we have only 2 signal points, S1 of t and S2 of t, right? And when you are capital M is equal to 4, then we have 4 phases, and we say it's QPSK, quadrature phase shift keying, QPSK or quadrature phase shift key, and we have 4 different phases, and we have 4 signal waveforms, S1 of T up to S4 of T, 4 signal waveform. Similarly, you can have the M value can be 8, and then you have 8 PSK, and so on, 16 PSK, depending upon the value of M. So you have M, when you say capital M, these are capital M different phases. So you have capital M different phases, because each signal differs from the other signal by its phase. Now, in the next video we will try to find out the Euclidean distance between the signal points of M array PSK. So we end up over here, and we will move to the Euclidean distance in the next video.